Welcome to Computer Systems 214. Today we're busy with Lecture 15, which is on one of my favorite topics, finite state machines. And today will be the first part, and then in the next lecture we will look at the second part. So in general, what we'll cover is just what is a state machine, how does it work, what is the principles behind it, because we're really now building on those sequential synchronous circuits that we developed or started to develop earlier. And we'll be looking at two types of state machines, just in terms of oversight. We'll look at Moore machines and Mealy machines. And then we'll do an example, just to help you understand what it's about. And then we'll finish off with just a simple design procedure, which will come in very handy when you have to make your own one of these. It's a structured approach to designing state machines. Now, before we launch into the detail, I just want to give you a quick oversight to explain to you where we're heading and how all of this hangs together. All right, so the most generic type of state machine is as follows. You have what we term memory, and this memory is the thing that remembers the state. It's the thing that remembers I am currently in a state. So for my body, that'll be I'm in a sleeping state, I'm in an awake state. For a vehicle, it'll be I'm in a driving state, I'm in a stopped state, I'm in a turned off state, I'm in a turned on state. For a passenger aircraft, it'll be I'm on the ground, I'm in the air. I am igniting, or I'm flying through a storm, so I need to ignite the igniters all the time so that the engine doesn't go flame out. Or I'm flying, I'm still ascending, so I need to apply quite a lot of fuel, so to get extra thrust. It's about remembering what the state of the current system is. And the purpose of these state machines is that they help an electronic system mimic or mirror or control something in the real world or something else that is also going to have different states. So that's what we want to get to, something that behaves differently under different conditions, and that which condition is saved by this memory module. So this memory module is, I hope you can guess, is basically just D flip-flops. So D flip-flops, they remember what is the current state, and then typically this has quite a large number of flip-flops to remember all the states. So that memory or that condition is stored in a flip-flop or a set of flip-flops. All right, so this is the thing that remembers our state. This is the memory, the state memory. Then this state has certain outputs. In each one of them, let me rephrase actually. In each one of the states, the outputs are a certain something. So the example that I typically use in my classes, it's like a baby. When a baby is in a sleep state, what you get out, the outputs are snoring noises or sleeping noises or deep breathing. So these outputs, they need to be generated based on the state. So what we have on this side is what we call output logic. So this is output logic, and they are the things that determine what is the output given the current state. So it'll evaluate the state and then say, given that state, the output is a certain something. If it's, for example, a baby, again, if it's in an angry state or an unhappy state, what you'll get as an output is a lot of crying, a lot of unhappy noises. So this logic here, the output logic, that says, and this is just combinational logic. This here will say, depending on what the present state is, there will be certain outputs, and this logic basically converts the present state into a certain number of outputs. Then what we also have is this state needs to move from one state to a next state. So it can't just stay in the same state, otherwise it's just combinational logic. It needs to move into different states. So it moves into a different state by considering two things. There are inputs, and it uses whatever is on the output. So I'm going to draw that like this. It considers what is happening on the inputs, and it also considers what is the current state, and it then gives out what should be the next state. So this part here we call next state. This we call current state or present state if you want. And this logic here we call the next state logic. So the way that this whole thing works is it looks at the inputs. Depending on the inputs and the current state, it then decides what should the next state be when there's a clock signal. So all those flip-flops change when there's a rising edge on the clock signal. Again, in the baby state, let's consider it a baby. If the baby is currently in an asleep state, the state is asleep, and then let's say as an input you are clapping your hands. That means the clapping of hands input and the sleeping input here will present here as a becoming awake, so awaking. So the next state will be become awake. So if a baby had a clock, when the next clock edge comes in, it'll go through and say, you are now awake, baby. Or if the baby's hungry and crying, so the baby is hungry, the output is crying, so this converts hungry into crying. Then you feed it with food, so the input is food, then the next state will be awake and happy. So when there's a clock edge, it'll clock through and then the baby's awake and happy. Then if you provide as an input, so it's awake and happy, output sounds happy sounds, whatever babies do when they're happy. When it's awake and happy and you provide maybe a nice lullaby, then the next stage will be sleeping. So when there's a clock edge, which a baby doesn't have, then it'll turn into sleeping again. Okay, so this is the principle of where we're heading. And what we're going to do is I'm going to explain to you how to choose how many flip-flops you need, how to determine the next state logic to make this thing transition between states in an orderly fashion, and how to determine the output logic so that it presents with the correct outputs in the current states. And just one more thing that I want to mention is, if the output here is only determined by the input, if the output is only determined by the present state, it's called a Moore state machine. If there's a line here, let me draw it in a different color actually. If there's a line here that says, hey outputs, you're also dependent on the current inputs, then it's called a Mealy state machine. Right, so that's where we're heading. So now bear with me as we go through the details. So formally, a state machine provides a systematic way to design a synchronous sequential circuit given a certain specification. So you can see the first thing that you need to understand when you design these things is what is the specification, and then you can start to design it, and I'll teach you the process in a second. Then they're typically called, these synchronous sequential circuits are typically called FSMs or finite state machines, and let me tell you, they are ubiquitous. In every single electronic system that I've designed, I've had to implement a finite state machine. It makes everything a lot more reproducible, a lot more debuggable. It just makes everything simpler, and it gives you a lot of control as a developer. Now, what we're going to use as a convention is that our state machine has M inputs. So that's just what we're going to say. Capital M is what we're going to say how many inputs it has. It has N outputs. So M inputs, M outputs, and we're going to say, let's say that the number of bits required to represent the states is K outputs. So we have K outputs here of our memory, or K memory bits, N outputs, M inputs. That's just the notation that we're going to use. That's our convention. And as I said, we have different blocks of logic. We have the input, the next state logic. That's the first block of logic, and this is combinational. Then we have the output logic, which is also combinational. They're both combinational, and they depend on, the output depends on the current state. If it's a Mealy machine, if it's a Moore machine, if it's a Mealy machine, it also depends on the inputs. And the next state logic takes in the present state or the current state, and it also takes in the inputs and then spits out what the next state should be. And I think that's everything I had to say, except maybe that it's important to just remember the transition of that clock edge is what causes the state to change. So the active edge, either a rising edge or a falling edge, is the thing that causes the state to change. In my example here, I have a rising edge sensitive flip-flop, so it will change on a rising edge. Okay. Just going into a bit more detail, the finite state machine implementations are often used as digital control circuits. So as I said, you typically use these if you want to control something, either another circuit or if you want to control a vehicle or a braking system or a satellite propulsion system or a horizon sunset. So you use this to engage with either the real world or with another system, and that real world can also include humans. And essentially what it is it gives a brain, it gives the indication of what to do and when to do it. So when to present which outputs, and then depending on certain inputs. Okay, and then inside the state machine, as you'll see in your project as well, inside the state machine can be registers, shift registers, serial communications, counters, analog to digital converters. All of these can be put into a state machine, but the fundamental building blocks are the state, which is saved in memories, the input, and the output logics, which is combinational logic. That's the essence of it. That's the fundamentals of it. So as I said, there are two types. There's a Moore state machine, and it follows this. So this is a bit neater diagram that I drew earlier. It has inputs, it has the next state logic, the output logic. This presents you with what should be the next state when a clock event occurs. And then the current state drives the outputs through the output logic. That's a Moore state machine. This is the simpler one of the two for me. The Mealy state machine says, in addition to depending on the present state, the output can also depend on the input, which essentially means this output here is not synchronous. It means the output changes immediately when the input changes. There's no latching that needs to occur here. All right, no clocking, no flip-flop synchronous events. The input immediately affects the output. Mealy state machine. Right, so let's look at an example. So all of this was pretty abstract. Let's look at something concrete. In this example, we're looking at a traffic control system. And this traffic control system wants to control the traffic lights for two lanes that are crossing. The one is horizontal, the one vertical. And as you can see, we have 4 traffic lights. These 2 lanes have 2 sensors each, but they're actually combined. So don't get confused. That's TA. Those 2 make up TA, and the other one make up TB. So there's only 2 sensors that are going to present as an input into our system. And what our output has to do is to control the traffic flowing in that direction, actually both directions, and the traffic flowing in those 2 directions. So we'll have 2 inputs being traffic horizontally, traffic vertically. That'll be our sensors TA and TB. And then we'll have 2 outputs as well. The 2 outputs will be lights in direction A and lights in direction B. Now just pay attention. The author of the book has made this a bit more complicated than is necessary. They've said, let's make this output have multiple lines. So the lights will drive yellow, green, and red. And instead of using 3 wires here, they've used 2 wires and said, let's use a binary encoder there. So it complicates things more than what it needs to be. Just for yourself, remember, this may as well have been 3 lights, 1 for red, 1 for green, 1 for yellow, 3 lights, 1 for green, red, 1 for red, 1 for yellow, or amber. Okay, and the logic that this thing employs is it'll start saying one of the roads has right of passage, so one of them is active, and then it'll say it only must transition to turn the other light green when there's no more traffic in the one direction. So the book doesn't say that explicitly, it's implied, so that's what I'm telling you now. It says if this light here is green, if that's allowing traffic in those 2 directions or in that general road, then it's only going to stop doing so when these sensors both say there's no more traffic there. So the reason I'm hammering on this, the reason I'm going on about it, is because understanding the fundamental requirements of the circuit is crucial for designing the state machine. If you don't understand these fundamentals, designing the circuit is going to end up a mess. So we need to nail down exactly what is meant before we can start to design the circuit. Otherwise, you're designing something that may be wrong. Okay, so that's the fundamental principles. 2 inputs, we have 2 generic outputs, and each one of them has 2 lines. The 2 lines decode red or yellow or green. And then we have a reset, and we have a clock, which is the thing driving the state machine, causing state transitions. Okay, So the first thing that you do when you have to design this is you start with a state diagram. And this state transition diagram, actually, the state transition diagram is the thing that, if you get that right, everything falls in place. This is the most difficult thing to get right, and it's not that difficult normally to get right. But once you've done this, the rest is really just a recipe. So that's why this part of this is the most important. So the way to do this is you say, let's start out and put down the initial state, the initial condition in which things are. You do that by putting a circle. This circle here is what we call a state. That is one of the states in which my circuit can find itself. And you can see there's a little arc here. This arc says when there's a reset, in other words, we're starting from scratch, this is the state I want this whole thing to start out from. So this is the power on state. This is the initial condition, if you want. Then we say, okay, from the state, we have to either stay in the same state or go to a different state. So you can see here, we have an arrow here saying, stay in this state or transition to another state. This little arc says stay, this one says go, and right next to it is the conditions in which those transitions will happen. So let's just look at this. State 0 says LA is green, LB is red. So that's the initial condition. So important implied here is the outputs are shown inside the state. We say the outputs are listed inside the state. My state, I've given a name, it's state 0. And then it says while TA is 1, so while there's traffic in that lane, just stay in that state. Then, if there's no traffic in that lane anymore, and there's a rising edge, so the rising edge is not shown, it's implied. The rising edge is the thing that causes the transitions, depending on the inputs. If there's a rising edge and there's no traffic, then transition to state 1. And state 1 is where that light is yellow, so it's going to go red soon, and the other one is still red. Now importantly, look here, there's nothing indicated here, there's just the one transition, and this transition does not have any requirements. It doesn't have any, oh, TA must be 0, TA must be 1, TA must be whatever. This transition just happens, which means regardless of the inputs, regardless of anything, this state transition will happen. Just jump back real quick, I forgot to say something. If you leave this out, it's also implied that it'll stay in the state. So if I've seen people leave out the recursive arc here, if it's implied that it'll stay in the same state, you only have to show the ones that actually transition states. Anyway, so this one here will transition regardless. So for one clock cycle, it'll stay in the state, and then it'll move on into the next state. And the next state is where LA is then red, LB is green, and we're in state 2. Again, this stays in the state all the time. For every clock edge, or every rising clock edge, it stays here until such time as TB is 0. Let me also say, I've seen people indicate this like that as well. Instead of saying not TA, they would say TA is equal to 0 causes this to happen, or TB is equal to 0 causes this to happen. Anyway, if there's no traffic on TB, then it will do the transitioning here into state 3, where LA will become red, and now LB is 0. And again, the next clock edge, it'll transition regardless of the inputs. It won't even consider TA and TB. It just transitions, and it transitions into state 0, where LA is green, LB is red, and then it's back to state 0. So this is our state machine. And this, like I said, this is the most important bit to get right. If you get this part right, everything falls into place. So what happens now? Now we have to draw something called the state transition table. So you'll remember we had truth tables for combinational logic. And then when we worked with flip-flops and with sequential logic, we said we have characteristic tables. Now we have something called a state transition table. And the way this table is set up is it has on the left the states. So for each one of the states, we have certain inputs that leads to certain next states. This is my state transition table. So the way to read this, if I'm in state 0 and TA is 0, it doesn't matter what TB is, it'll go into S1. Then, if current state is 0, I said then, don't worry about the then. Then, if I'm in state 0 and TA is 1, I'm staying in state 0. If I'm in state 1, it doesn't matter about the inputs, I'm going to state 2. If I'm in state 2, it doesn't matter about TA. If TB is 0, so there's no traffic in lane B anymore, then I'm going to go to S3. S2 will go to S2 if there's still traffic in B, and S3 will always go to S0 regardless of the inputs. So this here is my state transition table, and that I get directly from my state diagram, my state transition diagram. Now, what we do is we give these concrete values. So up to this point, it's pretty abstract. We've given state names here, but that doesn't mean anything in terms of digital logic. So what we do now is we say, let's give each one of those states a number. S0, we're going to give the number 0. The reason we give it 0 is because when we reset the flip-flops, we want to be in state 0. So we make that 0. The other ones you can number as you please, but typically you number in the sequence in which they will happen. So maybe it's also important to point out at this stage, many state machines actually do things like this. We have crossing in between. It's not always as nice and circular like this. Actually, it's usually not as nice and circular like that. But anyway, so you can number these then. We number S1, S2, and S3, give them each a number. And then what we do is we also just specify for the lights. As I said, the author of the book overcomplicated things here. He said, let's give a code to each one of the colors as well. So instead of just having one line for green, one line for yellow, instead of having one line for green, one line for yellow, and one line for red, he said, let's give each one of them a code. So now we have 0, 0 meaning green, 0, 1 meaning yellow, and 1, 0 meaning red. So now we've got everything coded. Now hopefully you should understand at this point, because we have this table, the state transition table, and we have this output encoding as well, we should be able to transfer this table into a Kano map and then just derive the next state logic. And because we have these coded as well, we can use the current state versus what we expect the lights to be in those states to draw up another Kano map to derive the output logic. So the next state logic will determine from a Kano map that we get from here. The output logic will determine from a Kano map that we get from whatever the outputs were in each one of the states. And then this coding that we introduced here. Okay, so what we do now is we take that into a Kano map-like table. And just to refresh your memory, we have this is the state machine. We have next state logic, output logic, and the memory that remembers what the present state or the current state is. Now we're going to develop this next state logic using that state transition table. So we use, as I said, we use the codes for S0. So this is just S0, S1, S2, and S3. So exactly what we had on the previous table, we're just written down using the codes. So just look at this. If you just consider S apostrophe 1 now, S apostrophe 1, S accent 1, or the next state most significant bit, this logic here must be 1 for those 3 ones. So we're just going to write it down at the table. This 1, just looking at what changes here, is not S1, not S1, S0. So that describes this one. Then these ones, you can see what drives them. Well, those two are different here. There we go. So if you want to write this down, you can write down it's not S1, it's S1 not S0 with a not TB, and an S1 not S0 with a TB. Those 3 ones are described with that function there. All right, then moving on, this function here, the least significant bit of the next state logic is this column here. And if you think about this one and that one there, this is simply equal to the AND of the two inverses. And this one, it's actually there. It's that term there. All of them are 0. And then the other one here is just where the present state is S1, not S0, and not TB. So that makes up that term there. And that really captures the whole thing. Now, this describes the next state logic. So if you were to then put those two functions in there, they describe the two lines that'll move there to say what is the next state. Then we go to the output table. So now we have to derive what the output logic is. So I just copied that whole output encoding here to refresh your memory. If we're in state 0, 0, just going to quickly scroll back. In S0, 0, you can see we're in green for LA and red for LB. So what we have is green for LA and red for LB. If we're in state 0, 1, it is yellow and red. If we're in state 2, it is red and green and red and yellow for the final state. So just doing the same thing now, if we were to write this down, LA, that's just the first bit of the light A, the most significant bit, you can see that is purely equal to S1. So that's S1 here. LA0, if you look at this, this is going to be 1 only in that condition there. So that's not S1, S0. There we go. Then LAB1, this is equal to a 1 here. So that's just equal to not S1. And LB0 is equal in this case, which is the AND of those two. So that's just the AND of those two. Okay, so that then, just jumping back here, this describes our output logic. So there are two buses, each with 2 bits, and they drive the output logic, and this describes the light A logic, this describes the light B logic. And this is how you draw that then. So these are the formulas we just derived for the next state logic and for the output logic. So if you had to do this, we obviously have the state register, the thing that remembers what state we're in, having 2 bits. And the next state logic, which is this logic here, is described by that function and that function. Let's just look at the easy one first. This is not S1, not S2 with not TA. So that takes, if you look here, that's S1. This is S0. And this is TA, and they're all inverted and then ANDed and sent into an OR gate with S1 not S0 and not TB. ANDed together and then ORed, that drives that drives the next state S0. Interestingly, this is actually an XOR gate, so you can go in the logic if you like, go and look at the logic if you want, but this is purely an XOR gate there. So we've replaced this whole thing with just an XOR gate. If you expand this term once, you'll find this is just an XOR gate. So just rewrite this with a TB and a not TB, once with a TB and once with a not TB, and you'll see this is just an XOR gate. So the next state, most significant bit, is just driven by an XOR of, as you can see, S0 and S1. Okay, and then the output logic. So this is the output logic, and as you can see, we have those 4 functions here, and they take the current state and they just then drive out the A light and the B light outputs. So it's as simple as that. Now we get to the timing diagram. So this is very important. This is where you then analyze the circuit to confirm that it works, and if it doesn't, you go back and fix. So just a few things to note here. We have the clock signal, and you should now realize that that was a rising edge sensitive flip-flop that we used. So on each one of those rising edges, it'll consider the next state, put it onto the current state, but only if it changed, right? So it'll copy and paste it every clock cycle, and if it changed, then the current state will change. So in terms of the first step, we have the reset here. Because we have the reset, we didn't know the values of any of the current state or the output values. So that reset caused that the states turn to 0. So state turned to 0, state turned to 0. That is my next state and my current state. They're all equal to 0. Because the current state is equal to 0, the next state is equal to 0. So let me just show you what I mean there. Because the current state is 0, the next state is also 0 when TA is equal to 1. So let's just look at this. When TA is equal to 1 and my current state is 0, then the next state is also 0. And then in the first state, my 0 state, I have a green light on LA and a red light on LB. Next thing we need to consider is the rising edge here. So on this rising edge, we're still in the reset. Then on the next rising edge, as you can see now, TB is 0. That does not affect the transition at all, so everything stays as it is. On the next rising edge, as you can see, TA is still 1, but TB is now 1. Nothing changes. However, when TA drops, state 1's next state, this next state, changes to S1. Let's just look at this. At least the next state changes to S1. Just want to show you what I mean. So this is the logic. When the input changes, the next state changes immediately. It doesn't wait for the clock. It doesn't wait for the register. It's not synchronous. So the input, when my current state is 0 and the next state is equal to, the input TA is equal to 0, the next state changes to 1, which is why this change in A resulted in the next state being 1. Right, then we have the rising edge. So this is where the flip-flop then clocks it through. On this rising edge, you can see what happens now. Sorry, I'm at the wrong rising edge. On this rising edge, then, the state is clocked through. This S1 is clocked through onto current state. That then changes. Because current state changes, the light changes to yellow. So now we're in state 1. In state 1, we have another rising edge. Because of this rising edge, the state changes again. And this state change happens to state 2. So the current state changes to state 2. Let me also just take a step back real quick. In the state 1, because this changed to state 1, and we configured the system to change into state 2 regardless of the inputs. So the output changed to yellow because we're in state 1, but then the next state immediately changed to state 2. Just going to show you in the table why that is. So in state 1, the next state changed to state 2 immediately. So this next state logic took that state 1 in and said immediately, hey, next state is state 2. So now it changed to state 2. And then on the next clock, that state 1 changed to state 2. And that's changed to state 2, modified light A to red, modified light B to green, and only when TB changed to 0 did the next state change to state 3. On that rising edge, that state 3 is clocked through onto the current state. So now current state is state 3. In current state, the next state is S0 regardless of inputs, just because it's there for one state. And the lights turn to yellow for LB. They're still nice and red for LA. Then, when there's a rising edge, that state 0 is latched through or clocked through onto current state. And in current state, the light for A is green, the light for B is red. So that's quite intense, but this is something you need to do to validate that your circuit actually behaves as intended. So what's the design steps? First step, understand the problem. Get the specification of the circuit. Then you draw a state diagram starting with the starting state. So you decide, where do I start? Just draw a diagram. That's where the reset starts. And then you go and decide which states must it transition into. For each one of those states, then you define, for each one of the states, you define what the outputs are in that state. So what's the output supposed to be in that state? Then you look at the transitions and you say, for each one of the transitions, what is driving that transition? actually you should have done that before you decided the output state. So for each one of the state diagrams, you decide what is driving that transition, and then you do what are the outputs in each one of the states. Then what you do is you take that state diagram and you convert that into a state transition table. And in that state transition table, you have to show the next states depending on the input and the current state. And then you also do what the outputs are depending on the current state. Then you could also minimize the number of states, but we don't deal with that in this module, and that's a bit advanced. And then what you do is you enumerate, or you give a number to each one of the states, and if necessary to each one of the output conditions. You give a number to it. As soon as you've got the state transition table and the output combinational logic table or truth table, then you use these codes that you've introduced to then draw up either a corner map or just read it directly from that table, and you make the combinational logic that drives the next state and the combinational logic that drives the output. Then you implement the circuit, so you make it, you design it, then you either simulate or actually build it and test it, and then you analyze the timing diagram to see that it behaves as it's supposed to. There's an alternative way to draw that state transition and the output table in one table, and some of the textbooks do it like this. I prefer this method actually, just because that's what I am used to. In this one, you draw the present state. For each one of the states you give a number, and then you say the next state is something, and that something depends on my inputs. The input can either be 0 or 1, and depending on 0 or 1, it's either going to go 0, 0 to 1, 0 or 0, 0 to 1, 1. So this is not the same example we had earlier. It's a totally different example, just a diagram randomly plucked from a book, okay? But it's saying the present state or the current state will transition into one of those two depending on what the input values are. And this will transition either not or into the 0, 0 depending on what the inputs are. This will transition either there or there. This will transition either there or there. And then for each one of the states, we have an output condition. So this is a bit, I think this is a bit simpler, but the textbook that we have currently prefers the other one that I just showed you. So in the next example, on the next slides, we'll do a few examples of Moore and Mealy state machines. That'll go into a bit more detail. Thank you.